buckled up? I hope so. Those were my parting words from my last episode and are very apropos because since then I've encountered quite a few marvelous and yet simple experiments that will necessitate a solid and firm grasp to your chair. So here we go with 3 more simple experiments that show that our universe is electric. Experiment number 1, the electroscope. Have you ever thought about what static charge looks like? Even as I write this sentence down, autocorrect is telling me to type astatic charge instead of static charge. But I actually meant static charge. Why? Because astatic charge is, in my experience, a misnomer. There are a plethora of charges which make up astatic charge, and they're about to become visible. So for this first experiment, all you will need is a small piece of cardboard, like a side of a Pop-Tarts box, maybe a shoe box, or a cereal box would work great. You need tape, any type of spot of glue, a dab of honey will even work. The next thing you'll need is a small, thin strip of tissue paper, wrapping paper, or just paper. That thin, small strip will be about 1/4 of an inch to 1/2 an inch wide and probably just as long as your piece of cardboard. You'll also need a PVC pipe around 12 inches long and a plastic ruler. Now, this is the critical part, and I'll explain why a little bit later. Now, right here, I have to stop and give a shout out to Professor Andre Koch Torres Assis at the University of Campinas, São Paulo, Brazil, for his assistance and guidance and instruction with this. In fact, if you want more of both Andre and myself, please click on over to the Brainstorm with Sparks and Finn. It's a podcast where me and my co-host, fellow Thunderbolts contributor Matt Finn, spend 2.5 hours talking with him. And we might even make a few jokes as well along the way. What we're going for here is a Smurf-sized picketing sign. But instead of words of rage and scorn, we'll just affix the small strip of tissue paper vertically, like this. Voila! You now have an endoscope. No, you don't have an endoscope. You have an electroscope. Here is where things get interesting. Prop up your device any way you can. You can get inventive. Just stick the ruler inside maybe a bunch of sand or in between some rocks or on a science stand. Anything. Like I said, get inventive. Take the pipe, the PVC pipe, and rub it quickly on your shirt sleeve or a blanket or a cat. Then touch the pipe to any edge of the cardboard electroscope and rub the pipe along the entire length of the electroscope. This is also critical, as the static charge you build up on the pipe by rubbing it doesn't move. It is static, so in order to transfer this charge, you need to be the one to move it, or at least the pipe. Now, when enough charge gets transferred from the pipe to the cardboard or the electroscope, the ribbon that you've attached in the middle of it will lift away from the cardboard. Please pay attention on how many times it takes to rub and transfer before the ribbon moves. That has some interesting things associated with it. And here, like I said, is where it starts to get more interesting. Now, please note, if the ribbon rises in one full piece or only half of the ribbon rises, and whether you need to keep adding charge to make it fully release and rise all the way. The question that is anathema to science is why? Why do the static charges seen here on this electroscope and elsewhere seem to form islands of opposite charge within a sea of attractive charge? That middle piece of paper only rises halfway and then it goes full way. And that's what I'm asking about. Now, I've puzzled on this for months when suddenly I realized that Ito Kull's SAM model gives us the answer. And that answer is nuclear electrons. In his model of the atom, there are areas in which a single proton would naturally be attracted to the nucleus of any atom. This window is the growth area of any nucleus of an atom. this window is the island of opposite charge. In this case, negative, because of the nuclear electron in a sea of positive charge, the surrounding protons. This is clear to me and not so much to those who I've shared it with, so take a look at this. Okay, let me see if I can demonstrate what I mean by the islands of charge. We're going to grab one of my display magnets. This is, of course, carbon in the Edo-Call model. Some of my fun stuff. We're going to set that right there. Okay, so this is, like I said, the SAM model of the atom, saying essentially that the nucleus of atoms has a specific shape. It's not just a hodgepodge. Well, look at this. Right here and here and here, we can imagine these as protons. Now, in reality, they are magnets, so this model doesn't actually work. And you can see that if I use these. And I know they look pretty trash because I use these a lot for this demonstration. Of course, the colors represent the poles, so we've got a north pole connected to a south pole. Here, it's a little bit muddied. Here, it's very, very clear. But just like this, you have an island right here in the middle. Well, in Ito's model, there are nuclear electrons. So if these represent protons, and now I realize that the protons don't have a side-to-side pole, so don't come after me for that. But right there is a space, and right there is a space. Inside, or in that space, would be the nuclear electron, okay? Which is equally drawn to this guy, and to this guy, and to this guy, which means that they would not combine. That if you were to look at a picture of this, if you could just see the fields of it, you would see this ocean of positive charge and a little island of negative charge right in the middle. And there, and there, and there. It's an island of separated charge. There's another possibility as to why positive and negative charges can sit next to each other like islands in the ocean instead of just combining and becoming neutral. And it came to me just as I was sitting here writing this episode. And that is, in a word, or two words, fractured geometry. The charge which accumulates on the surface of a rub pipe in the aforementioned experiment is sitting on an imperfect or fractured surface. Now, to us, it looks homogeneous. But on the molecular level, the lattice shape of the molecules is anything but. It's not perfect. It's broken up, which would mean that the charges that spread along its surface must be fractured or separated as well, meaning that positive and negative will be sitting next to each other. Simple, just like most of the stuff in the electric universe. Now, for those Douglas Adams fans, the answer to all of this isn't 42, but the answer is rather charge and geometry. Okay. Now, with your electroscope charged, meaning that the strip of tissue paper is being repelled from the cardboard, discharge the electroscope with a host of different objects by simply touching the said object to the cardboard. Why? Because the results you're going to find out kind of defy your modern understanding of what is a conductor and what is an insulator. Andre Assis has turned this little thing into somewhat of a game and has demonstrated it with Matt, Finn, and I on our podcast, Brainstorm, Sparks, and Finn. Yeah, no other shameless plug. Now, I don't want to spoil the results, but please do it yourself. The results are pretty surprising. Experiment number 2, visualizing lightning flashes. Grab a computer, rather sit down at a computer and open a browser of your choice. Then type in the following URL, star.nestis.noaa.gov/goes/conus_band.php. Now first, press the blue button labeled Enable Auto Refresh. Second, observe that there's a window labeled GLM FED +3 Geocolor Lightning Flash extent over geocolor. Third, on this window, select the first option labeled Animation Loops. Fourth, the map should open and begin playing a repeated loop. Fifth, find the small drop-down window called Loop. Sixth, select the largest number your computer can handle, and it may take up to 30 seconds to load in these larger numbers. I use 240. What that does, it just creates a huge window of time that you can use to make this observation. Highly recommend that you use as big a number as you can. Like I said, it maxes out at 240. What you're watching is a fantastic map of the east coast of the United States of America, taken from a geostationary satellite called GOES. And it's a part of the GOES-R constellation of weather satellites orbiting 35,786 kilometers, or just over 22,000 miles above the equator. Now, geostationary means that it's spinning with the Earth. And not to be left behind in the social world, even these science satellites use filters. The filter you're looking at, as some of you have already figured out and noticed, tracks and visualizes lightning flashes. Now, as cool as all this is, I highly encourage you to click around on this website to take a look at all the other maps and filters. Please notice that the lightning flashes are on this particular map, but not on all the other ones. As you're watching that, do you see anything interesting? Look for a little bit longer. Now, I'm not going to reveal what I think I see here, but I'll rather leave it up to you to tell me in the comment section what you see. I will tell you, however, that I've shown this and discussed this with Michael Claridge and Andy Hall, among others, and they tend to agree with what I observed, even though it defies current understanding of lightning and clouds. Experiment number 3, the Comb Insulator. Water is neutral, balanced charges, so we're told. I wonder what Gerald Pollack would say about this. Actually, I know exactly what he'd say. He would say, are we talking about easy water or not? For anyone interested in charge or water, or just perk up their ears whenever they hear Gerald Pollack's name, I highly, highly encourage picking up his book, which is also an audiobook, and it's called The Fourth Phase of Water, Beyond Solid, Liquid, and Vapor. This is easily in the top 3 books I've ever read. The answer may still not be 42, but The Hitchhiker's Guide to the Galaxy still reigns as number 1 book for me. Sorry, Gerald. All you need for this experiment is a tap of running water and a comb. Turn on the tap and produce a small stream of coherent water. Rub the comb through your hair or on the hair of an unwitting assistant or a cat again, and bring the comb near but not touching the stream of water. What happens? Well, I'm not going to tell you. I'm going to make you go out and do it. That's pretty cool, huh? Water is clearly not neutral. Now, there's a lot to be said about this property and is demonstrated again on every single water heater tank in the form of a sacrificial anode. Look up that one when you get a chance. We have just come full circle back to the plastic comb, because that fulfills the same role as the plastic ruler in the electroscope experiment. It acts as a true insulator. Insulators are not what we think they are. Andre Assis, you nailed it, buddy. Please go spend some time and check out these experiments. They're really easy to do, especially that water and comb one. You'll be surprised what you find. There is so much more we could say here, and we will. But this will at least get you started on that awesome, awesome adventure that is our electric universe.